Hello everyone, I'm presenting to you an in-memory analog computing coprocessor for energy-efficient CNN inference on mobile devices. This work comes to you as a collaboration between the Computer Science and Engineering Department of University of South Carolina and the Department of Electrical and Computer Engineering at Lehigh University. In this paper, we are proposing a new SOT-MRAM-based neuron to realize the sigmoid activation function. Then we use the new designed neuron and integrate it with a compatible SOT-MRAM-based synapse to build an in-memory analog computing. Then we show the ability of using our proposed iMac to implement a multi-layer perceptron. Then to be able to run convolutional neural networks or larger algorithms of deep learning, we integrate the low-precision iMac with a high-precision CPU to build iMac CPU that can run the CNN algorithm very efficiently. At the end, we present our experimental results and compare them with the state of the art. Throughout the presentation, I will start with the necessary background required to understand the contribution. Then I will explain the SOT-MRAM devices that we are using to build our proposed synapse and neurons. Then I will show how we can use the proposed SOT-based synapse and neurons to build our proposed iMac architecture. After that, I will go through the integrating the CPU with our iMac to accelerate larger AI algorithms such as the CNN. Then at the end, conclusion and future work are shown. This work is driven by the deep learning applications. As you might know, deep learning algorithms have been widely used in many applications and systems, including computer vision, smartphones, self-driving cars, and many more. Unfortunately, the current CPU-GPU hardware is no longer efficient to run these algorithms, and this is due to the data movement bottleneck. Data movement between the processor and the memory is very expensive in terms of the power consumption, and it takes also very long time. As an alternative approach to solve this expensive out-of-the-chip data movement, near-memory computing is proposed. Near-memory computing means that we have the processing elements on the same chip with the memory, so the data movement between the processing elements and the memory is not that expensive. It's still there. There is still kind of communication between the processing elements and the memory. That's why it's not very enough. Therefore, we see that in-memory computing is a solution. And in-memory computing basically is moving some sort of computation to the memory itself. So instead of running everything on the processor, we move some kind of computation to the memory, so the memory itself can do both things, can do memory stuff such as storing and retrieving the data, as well as processing some kind of operation such as multiplication and accumulation and some sort of other functions. There are many types of in-memory computing that have been proposed in the literature, and they are digital-based in-memory computing, where the memory cells are built to implement Boolean operations. This can be used only for binarized neural network. On the other hand, some authors propose the mixed signal in-memory computing, where some operations such as matrix multiplication and accumulation operations are computed in the analog domain, and the other activation function, for example, or other operations are computed in the digital domain. This approach requires signal converters to convert the data from the analog domain to the digital domain. And unfortunately, signal converters are big and very power hungry. So to get rid of these converters, we propose here an in-memory analog computing, which we call here iMac. iMac can compute both the MAC operations as well as the activation function in the analog domain. So there is no need to include the high power and big size signal converters anymore. Many devices have been proposed in the literature to design an in-memory computing architecture, including memristor, PCM, and many other devices. Here, we choose SOT-MRAM as our iMac building block, which we could use to implement synaptic connections as well as the activation function. However, using different memristor devices gonna have the same structure. SOT-MRAM devices, as you can see, is composed of two ferromagnetic layers separated by a thin oxide layer, and SOT-MRAM device has two resistance levels determined by the magnetic direction between the ferromagnetic layers. For example, if the magnetic layers are in parallel, the device will have high resistance, and if they are in opposite direction, the device is gonna have low resistance value, according to the equation that you can see here in the slide. As said, many authors proposed the hardware synaptic connections before. They use different technologies in their design. For example, they use memristor, they use RAM-based synapses. Here, we use the SOT-MRAM to build the synapse. In neural network, the synapse mainly acts as the weighted connection between the neurons. As you can see here, this is our SOT-MRAM-based synapse. It has two SOT-MRAM devices, which we should configure them to realize the weight -1 and 1 according to the table here. In the configuration phase, we basically enable the write word line and disable the read word line, and using the bit line and the select line to configure them either in a high resistance or low resistance to realize the negative weight or positive weight. Here, this is the analogy circuit schematic of our synapse. When apply the input X, a positive and negative currents go through a differential amplifier, and then this differential amplifier compares them, and the output of the amplifier is proportional to the input X multiplied by the differences between the conductance here. For the sake of compatibility, we are proposing a new SOT-MRAM-based neuron realizing the sigmoid activation function. Here in our design, we use two SOT-MRAM devices with different values in series connection. This connection creates a voltage divider here, and this voltage divider reduces the linear region of the CMOS-based inverter's voltage transfer curve. As you can see here from the SPICE simulation results, we can get the sigmoid activation function here through changing the operational region of these transistors of the inverter. SPICE simulation results show that our proposed SOT-MRAM-based neuron consumes around 64 microwatt, and from the layout design, it occupies around 0.02 micrometer square. We compared our proposed neuron design with the best resistive device-based neurons, and we found that our proposed neuron achieves around 74 times and 12 times more efficient than those neurons in the literature. Until here, we show you how we can use SOT-MRAM device to build synapses and also to build the neurons that realizing a sigmoidal activation function. Then I will go through the IMAC architecture, how we can integrate the synapse and to build synaptic connections and to realize the multiplication and accumulation operations, and also how we can use the synaptic connections and integrate it with the neurons to build the in-memory analog computation to realize the multi-layer perceptron. Here, we integrate the SOT-MRAM-based synapses and neurons together to build an in-memory analog computing architecture. IMAC is composed of a network of tightly coupled IMAC subarrays, and in each subarray, the synaptic connections are designed in the form of crossbar that can implement the matrix multiplication and accumulation operation. As explained before, we need to configure the SOT-MRAM devices according to the network weights to realize the synaptic connections of the neural network. For the sake of simplicity, we only show the reading path here. We use the bit lines as input to the IMAC and activate the read word line and disable the write word line to be in the inference phase. The output of the synaptic connections are connected to the neuron that we are proposed to realize the sigmoid activation function. Here I'm going to show you how we can use the in-memory analog computing architecture to realize the multi-layer perceptron. We tested a 784 by 16 by 10 multi-layer perceptron to implement the MNIST classification task. We realized the multi-layer perceptron using our proposed IMAC architecture. Each IMAC subarray computes the MAC operation and neuron activation functions, and then pass the result to the downstream IMAC subarray to compute the next fully connected layer. Then at the end, we could realize the multi-layer perceptron throughout this architecture. Here, if you want to have a realization of the proposed IMAC and to see the benefits of the IMAC architecture through the necessary simulations, we developed a Python-based framework that we call IMACSim. IMACSim can get the weights and bases from a third-party platform such as TensorFlow or PyTorch, for example, then map these weights and bases to synapses and neurons to build the IMACSim arrays. Then, the same framework integrates these subarrays to build IMAC architecture SPICE model, and using the SPICE framework, we can test the accuracy and power consumption and latency of the IMAC architecture and print them to the console. Here, to fully utilize the IMAC feature, we propose the hardware-aware learning algorithm for multi-layer perceptron, in which we binarize the bases and the student networks, and then use the sigmoid activation function instead of binarizing it to reduce the information lost in the binarized activation functions. and then we can get higher accuracy using the iMac. To see the numerical benefits of the iMac-based multilayer perceptron, we tested our proposed iMac-based multilayer perceptron, and our simulation showed that we could achieve 85.56% of MNIST classification accuracy for a network of 784 by 16 by 10. Then we compared our iMac-based inference with the Intel CPU and other in-memory computing architecture. We found that our proposed iMac architecture achieves 2, 3, and 4 order of magnitude improvements compared to the IMC, MREMA, and the CPU respectively. Also, our iMac could execute one complete recognition task in less than 40 clock cycles of Intel Core i9 CPU, while the CPU itself takes 1 million of clock cycles to implement the same task. So far, we have seen how to use iMac to realize multilayer perceptron. Here, I'm gonna explain how we can integrate the proposed low-precision iMac architecture with the high-precision CPU to run larger deep learning models, such as the convolutional neural networks. Here, as you can see in this figure, we integrate the low-precision iMac architecture with the high-precision CPU on the same chip to form a mixed precision and mixed signal CPU iMac architecture. To implement larger algorithms, such as convolutional neural network, the CPU is gonna be responsible for implementing the convolutional layers, while the iMac executes the fully connected layers. In order to get rid of the data converters between the CPU and the iMac, we use a sine function at the output of the last convolution layer running on the CPU. We extended the x86 instruction set architecture to include more instructions called store iMac and load iMac to transfer the data between the processor and the iMac. And because the iMac latency is well defined, we use a counter that had the value of the well-defined latency that send a flag to the CPU to resume its computation. Again, when using the mixed precision CPU iMac architecture and to fully utilize the benefits of the hardware, we also propose a hardware-aware learning algorithm for convolutional neural network models. This approach, we can get the benefits of the hardware without compromising the accuracy. It works into 2 steps. In the first step, we normally train the full precision CNN model using the normal backpropagation learning method. Then in the second step, we divide the CNN into convolution layers and fully connected layers. We apply a sine function on the output of the last convolution layer and generate a new training dataset that can be used to train the separated fully connected layers. After retraining the fully connected layers, we can have high accurate CNN inference on the CPU iMac architecture. Here, we also implemented the limit for MNIST classification, and we could achieve 97.39% of accuracy. And we could also build VGG model for CFAR10 classification task, and we could achieve 92.87% of accuracy. As you can see from the figure here, the sine function is used at the last convolution layer to avoid using the digital to analog converter. And as we said, the digital to analog converters is big and consume high power. Here, we also use ChampSim framework to model the core, and we adopted the core parameters from Intel Core i7 processor. Also, we use iMac architecture that has 128 kilobyte in form of 4 512 by 512 bits. The size of the buffer between the CPU and the iMac is 64 bytes, which is enough to transfer the data produced from the last convolution layer in both VGG and Linnet model. Our simulation results show that we could achieve 11.2% of speedup for the Linnet model inference, while we could achieve 1.3% for the VGG model inference. We have also seen that the ratio of the fully connected layers to the convolutional layers affects the overall speedup. That's why we could only achieve 1.3 speedup for the VGG that has 15 convolution layers and only 2 fully connected layers. While, for example, we could achieve 11.2% of speedup for the Linnet model that has 2 convolution layers and 3 fully connected layers. And to realize the energy benefits of the proposed CPU iMac architecture, we use MacPath simulator to calculate the energy consumed by the baseline mobile processor. Also, we use CACT simulator to measure the cache energy consumption. Our proposed CPU iMac architecture could achieve 6.5% of energy reduction for VGG and 10% for Linnet model. It's worth noting that our iMac is consuming 97 nanojoule for Linux implementation and 512 nanojoule for VGG, which are negligible to energy consumed by other modules in the system. So far, we have seen how we could use the SOT MRAM to build synaptic connections and the neuron activation function. We could use the proposed neuron and synapses to build iMac unit that can realize the multi-layer perceptron and achieves order of magnitude improvements in the performance. We also show how we can use the iMac and integrate it with the CPU to build a CPU iMac architecture that can run larger convolution neural networks. The proposed CPU iMac architecture provides several possibilities for future work, including, for example, a design space exploration to develop CNN models optimized to utilize the CPU iMac benefit. We can also extend the utilization of the iMac to convolutional layers, so it can run also on a convolution layers through convolution unrolling techniques. If you want to get more information about our iMac architecture or our CPU iMac architecture and our project, please go to the website here. Here are the references, and thank you for paying attention.